we ran a tract-based spatial statistics analysis, the TBSS, on the participants. And so now we're going to look at the results and talk about some of the files a little bit. So now what I'm going to do is go to the on-demand service for research computing, and I'm going to start a console session. Here, 1 core, 4 gigabytes of RAM, 2 hours. You could do 1 hour, a little bit less time. It doesn't take a lot of time to do this. I'm using my personal account. You can use the class account, CLP7934. So I'll launch that, and then we wait while this session is queued up on HyperGator, submitted, and then run. So this is just like you writing a script, the submission script that you then do SBatch. And so we're doing the same thing, but submitting this GUI console session as a script, and you don't have to write the script that does that for you behind the scenes. So we can launch the console. And so the first thing I like to do is get to the location of the data. So CLP7934 share, homework data, and then I'll go into my folder and then TBSS. Within there, I type ls and we see 3 folders and 2 files. So the 3 folders are FA that was created, and that has a lot of the processed, almost all of the processed files. Orig data has the original FA files. So if we went into there and did ls, we can see a list. So this was a copy of the untouched files, FA files, and they're in there. And just as a reminder, how many subjects do we have? We have 14. We have 7 controls and 7 patients. And so those are our untouched data. So if you had to start over, you have all of your raw data there. Really what we're interested in is the stats folder. So I'm going to go into the stats folder. We can type ls, and we can see a number of files in there, all FA skeletonized. We have our con versus pat.con. So I'm going to run a command called cat, and that will just print the contents of that text file so we can see what they are. Number of waves, number of contrast 2. And so here's our matrix, 1, -1, -1, 1. So what we're doing, so this was the part of the script where we did design t-test 2. So we are doing a t-test on these data. And so whichever group was first, in this case, we're calling our control group. The first test we are doing is that the control group have higher FA than the patient group. And then the second test is the other side of that t-test, where the control group have lower FA than the patient group. So your 2 group, this is a t-test, are there group differences, and then we're looking at both directions. So that's that file. If we do the same thing for the mat file, we can see number of data points. We really have our 2 groups. So here are our 2 groups. And so we have 2 columns. The first column is which group are they in? So really the first group, they have a 1, and they're not in the second group. And here's a second group. They're not in the first group, but they are in the second group. So this was all created by the design t-test command. And so you could do this manually if you knew how to do it. You could also use the FSL GLM that we used when we did the voxel-based morphometry analysis. So these were created as part of our script. And then there's some other files in there. So what we're almost ready to do is we're going to use FSL's viewing tools to look at the results. So the first thing we need to do is module load FSL. So one of the things we can do is we could just type in FSL Eyes, and that's their current viewing software. They have an older one called FSL View. FSL View now is called deprecated. Now, of FSL View, the command still works, so we could possibly use that. But again, FSL isn't really updating the software anymore. Their FSL Eyes is a newer software, has a lot more features. In some ways, it's not quite as easy to use, but you can do a lot more with it. So we're going to use that one instead of FSL View. But FSL Eyes, we could just type in FSL Eyes and open it up. And then we can load in the data. And that's fine. But what I'm going to do is we're going to see if we can load in as much of the data as we can from the command line. So here's FSL Eyes. I'm going to just close that. And over here is what's called FSL Toolbox, Diffusion Toolbox Practical. So you could search for that, and you should get this website. But we're going to skip all of this because we've done most of this. The top two aren't relevant to the data we have. But we did the DTI fit, and then we ran TBSS. But I'm going all the way down to the bottom, and there's a command right here. And so this voxel-wise statistics on the skeletonized FA data, and that's what we ran. And we ran a step like this randomize, and we have our output. And so this contrast 1, again, we looked at those contrasts. We did 2. And 1, it's not young versus older in our case. It was our controls higher than our patient group. And so the raw unthresholded t-stat image is called TBSS t-stat1. And that's what we have over in our directory, TBSS t-stat1. So these are t-values. So we think about, okay, so what are t-values? And just to show you, here's our distribution. So if we're looking at the student's t-distribution, and just showing this as a refresher for statistics, what we're kind of interested in are this t-table. And we don't necessarily have to know these, but this is something to be aware of. So we have 14 participants. With 14 participants in a very simple t-test, our degrees of freedom is n minus 1. So in that case, our degrees of freedom is 13. And so here's our critical t-value of 1.771 for a 0.95, so a p of less than 0.05. Or if we want to be a little more robust, p of less than 0.025, and that'll give us a little bit more, it'll cut off a little bit more noise in the data potentially. And so a little more strict, because what we're really running are 2 one-tailed t-tests. And so in this case, we can kind of remember these numbers. We'll come back over here and pull them back in when we're looking at the results. We could also look at these corrected P, the TFCE, the threshold-free cluster enhancement, these corrected p-values. The downside of that is we only have 7 participants in each group. If you had a large sample size, at least 30 in each group, or 40 or 50 in each group, again, a bigger sample size, then we can be more comfortable using these corrections for multiple comparisons. The problem with a small sample size is that's going to, if we use these corrected values, then we'll be sure that we don't have any, we're pretty sure that we don't have any false positives, but we're going to be likely have a lot of false negatives. And so we're going to look at those as well, but we're going to start with these TBSS t-stat1. Now for a paper that you're trying to publish with peer review, you probably couldn't get away with just reporting these t-stat1 values. unless you were saying, okay, these are preliminary data. We only have 14 participants, 7 in each group. And as just pilot data, we're reporting this. Then you could maybe get away with it, but you need to be a little more robust. So, but those are our statistics, and we're not going to cover a lot of that in this class. It's not quite the purpose of this class. It's just this class is to give you a foundation for imaging, just so you're at least somewhat aware of the different tools that are out there. You've done these before, so if you go on to do it, or you're reading about it, you might recognize, oh, FreeSurfer, FSL, I recognize that, or Con, or some of these other tools. You recognize it and kind of understand some of the procedures that go in there, go in producing the data. But why I pull up this practical, again, you can get the link is up there, or you could search for FSL Diffusion Toolbox Practical, it would come up, is this command right here. So FSLIs with this flag, STD 1 millimeter, will load in a standard space brain, an M&I brain, that's the 1 millimeter brain. Then it'll load in a file called mean FA skeleton. So if we come look what we have a mean FA skeleton. And then this is saying it'll make that skeleton green, which is sort of FSL's convention. And then the range, it'll only show values between 0.3 and 0.7. And so it's truncating the value, meaning it's not going to, I guess it won't, it's not that it's showing values between 0.3 and 0.7. It's only going to have the range of the color vary between 0.3 and 0.7. And then it loads in a file called TBSS tstat1 and makes that a red yellow. And then the range of values for the coloring is going to bottom out at 1.5 and then top out at 3, meaning values of 3 or higher are all going to be yellow, the same color. And values below 1.5 would all be cut off. And so that 1.5, this will go back to our critical values. So really, we don't want a critical value that 1.5. If we want to be a little, we could stick with 1.5. Again, that's about right here. P of 0.9. We want to be a little bit more robust. So we're going to, we could increase it up to 1.771. And 3 we can keep. And then here they're also pulling in a corrected p-value. They used a different way of correcting for multiple comparisons. We did a TFCE method. And then in that case, so they're doing that as blue, light blue. In that case, their range of values of 0.949 to 1, because this one is essentially p-values, and we just want to show the top, the p less than 0.05. And that's how you do it, is it's not a direct, we don't cap out at 0.05 and just show between 0 and 0.05. We're showing kind of the reverse of that. And so 0.949 up to 1. And so most of this we can copy. I'm going to copy that first line. If we have those lines in there, it would copy it and be okay. Oops, I had that highlighted, so copy that. We'll have to put the text in there. Okay, so again, I'm middle clicking. You should be able to do the Control-C, Control-V to copy and paste. But again, this sometimes wasn't working for some of you last time. And then I'm going to get this next line, and we're going to ignore the last line. So I paste that in there, and I can middle click. But what I'm going to do is I'm actually going to put that in there one more time. But instead of red, yellow, I'm going to do this blue, light blue. And so what this is, and I'm going to change this to tstat2. Blue, light blue. And I'm going to change this to 1.77 to sort of match that t value. So what this is going to do is it will load in both of our tstat files, and they'll be appropriately thresholded to show us only areas where the groups are differing with the t values of 1.77 or higher. So we hit enter or return, wait while this loads. So again, you could just type in FSLIs and load all of this in manually, and that would work just fine. But sometimes it's easier just to have it all in one command. Okay, so this is loaded. So let's think about this a little bit. We'll walk through this. So what we have are, here's our MNI, and so that's the background, the nice brain. That's a T1 brain. And so that's just giving a nice backdrop. So I can click the little eye and turn it on and off, but we'll keep that on. And then we have the mean FA skeleton. That's that in green. And if we notice, we have a lot of blue and some red specks everywhere, somewhere. And so what does this mean? So the red specks, if we remember, that's our TBSS tstat1. And so what does that mean? So these are areas where our control group have higher FA than the patient group. That's what we were testing. And that's why it's important, as I said, when we're setting up the data, you want to make sure that the control group is first, or whatever your groups are, that you just have them all grouped together and you know which one is which and what you're testing. And so in this case, we were testing our control group have higher FA than the patient group. And we see there's a few spots where that might be the case, but remember, these aren't corrected for multiple comparisons. And why is that an issue? Well, what we're doing is for every green spot in this, what we call the skeleton, everywhere that we have a green spot, this is a voxel. And each voxel is what we are, so this is our skeleton of sort of core white matter in the brain that's overlapping between all 14 of our participants. And what we're testing is FA differences at each voxel, each spot in the brain. And we could sit there and count, and there are a lot in the skeleton. There are thousands of voxels in there. And so we're doing thousands of statistical tests. And just, if you know the statistical theory, we're going to have a lot of false positives, really, with this, because just going to be, something's going to show with the data and with the tests. And so what we do is threshold this. So again, if you were loading these data in manually, you can go to File, Add from File, and we can load them in, tstat1, tstat2. Maybe we'll do that for the TFCE ones. And then here are our min and max values. So min, if we put that down to 0, what do we expect will happen? We're going to see sort of red everywhere. And then if we put it at 1, we should have more areas where it's red. Notice we did 1.77 and they went away. If we want to be a little more robust, again, we find our other critical value. Let's do our 2.16 as our minimum. 2.16. Now we've been a little bit more robust. So these are data that with a small sample size, if we're talking about these as pilot or preliminary data, I would be a little more comfortable with publishing. Certainly this would be great for a grant submission saying, here's some possible evidence of some differences. And so that's T-stat1. T-stat2, so this is the blue one. So what is this showing? So this is showing, I have the threshold at the same, the 1.77. If we want the higher one, again, what's our value? 2.16. Be a little bit more robust. So now what we're showing is these were areas of P less than 0.025. You could also say, well, we're not correcting for multiple comparisons, so maybe we want to be even more stringent. So 3.852. Well, I'm just going to run this. I don't know what we'll get. 3.852. And then we'll put our maximum up to, actually going to go up to 5. So we get a little bit of variation. So in this case, we still see a few spots of differences. This is uncorrected P of less than 0.001, which is fairly robust, and those are even potentially publishable. If we did the same 3.852 for the T-stat1, now I don't think we have any more areas that are in there. So what that means is, so this patient group now, this T-stat2, these areas that are left in blue are areas where this particular group, the patient group, has higher FA than the control group. Now, sometimes you would think that's a little weird. A lot of times FA is going to be lower in a patient group if it's a group of individuals with Alzheimer's disease or mild cognitive impairment or schizophrenia or extended drug abuse or whatever we're interested in. We're probably going to see decreased FA or lower values of FA. These particular data are a little bit contrived, meaning that what I'm calling the control group just happens to be one group of adults, and the patient group is another group of adults, and they are different groups, but what I was calling control and patient was actually arbitrary. So we're just seeing a group difference here. And so those are some results that we might be reasonably comfortable with. And so we're seeing some differences here in white matter that's what we said near the sort of part of our cortical spinal tract. And so this is what you could do. You could do a screenshot and submit this for homework. You could do a built-in screenshot. It may or may not work. We've had some issues with that. But if you certainly do a computer screenshot, you would have this. You can turn off the crosshairs if you want it cleaned up a little bit. So now let's look at the little bit more robust data. So I'm going to turn off those two images and do File, Add from File. And now let's load in these two. So you can shift click to select multiple files. And so these ones are different. So what we need to do with these ones are threshold. So if we come over here to the practical, we could see what they're doing with, these are the corrected p-values. So the minimum is 0.949 to give us a p of 0.05. So as we're going to expect, so I've highlighted T-stat1, this corrected p T-stat1. Our maximum is 0.28. So what do we expect we're going to see? So I'm going to change the color first to red, yellow. And then I'm going to set the minimum to 0.949. And as we might expect, if the maximum value in there was about 0.28, we're not going to have any that are any values above 0.949. So we're not going to see any areas in the brain that are red, yellow. T-stat2, on the other hand, our maximum value is 0.957. I'm going to change this to blue, light blue. And so this isn't helpful. There's lots of areas of blue, but our minimum is too low. We need our minimum of 0.949 to show just P less than 0.05. And then our maximum, we can put our maximum up to 1 to give a little bit of range, not a lot of range. So this is that same area. If I turn this T-stat2 back on, and again, I turn this off, that's essentially that same area that we saw in both. And so this, with the T-stat2, we're seeing a few other areas that are disappearing in this corrected one. But these are pretty, this is pretty robust finding. So with a group of 7 participants, so we have 7 participants in one group, 7 participants in another group, and we're using a robust correction for multiple comparisons, and we're still seeing a group difference, that's where we start to think there's really something going on. Now, we haven't corrected for some potential confounding variables. It could be age, maybe it's education, maybe it's body mass index, or some sex or gender, some of these other things that can influence the results. But again, these are fairly robust findings if with a straightforward, maybe overly simplistic analysis. So that's how we look at the results and present results with TBSS. And so again, now we've looked at both uncorrected and corrected ones, and we've played around with the thresholding on them. And so what we're seeing consistently with the uncorrected and the corrected ones are some areas where one group, in this case what we're calling the patient group, really aren't a patient group, but one group has higher FA than the other group. And so that could be really interesting findings. So again, you can do a screenshot of this and submit it. If you're spending time to get this for a publication, you would probably do something kind of like that, where you're highlighting it. Again, we wouldn't have these values on. We wouldn't have both T-stat and the corrected T-stat. But we could do something like that and have a screenshot of this. We would save it here with the screenshot, and then that might be ready to be submitted as part of your publication. So we will end there. That was our example of loading in TBSS results to look at them. And there are more things you could do with these data, kind of beyond what we've done. But for the most part, a lot of TBSS analyses is you want this visual. And then we would comment and we would say, okay, so where are these? And if you're interested in where those might be, we can view we have to have it in the settings. Turn on what we call this Atlas panel. And we choose an atlas. So in this case, we need white matter. Now it's being kind of slow. So I'm going to do this white matter atlas. And so right here, so I have those atlas, JHU Johns Hopkins University, white matter labels and tractography atlas. So I've clicked in there. And so one, it's calling it superior corona radiata on the left. And then this other one, it's a probability. And so it's saying 8% probability overlap with cortical spinal tract, 3% with superior longitudinal fasciculus. So that's something that you could use these atlas information. Again, that was under settings atlas panel. And then I had to turn on these white matter atlases. And then that gives us a little bit of label. If you're wanting to write this up and say, you could say, well, now we're showing group differences in, you have the picture, but you'll say this is superior corona radiata, likely cortical spinal tract. If we click on this other dot over there, It's saying retrolenticular part of internal capsule. So it's just white matter, but really, again, now we're in what we're calling internal capsule. And if you know the anatomy, know what those are and maybe what they're involved in, but that's where you could get some information to write up and say, what are these areas, rather than just, here's a picture. And you could say, okay, this is part of internal capsule. This is likely part of somatosensory, the cortical spinal tract. And that's showing these differences. So that's using the atlas. And then we'll end with that, but hopefully that gives you a sense of tract-based spatial statistics. This is a really powerful tool, with the caveat that most of the analyses that we're doing, or this analysis, is FA, and so it's based off of what we call diffusion tensor imaging. It's overly simplistic view of the brain. It's shown to be clinically important, but it's not a perfect value to use. But we can go on and use some other diffusion-based values. That's well beyond the scope of this class. And then with that, we will end this presentation.